morning, everyone, and welcome to this coffee break. My name is Mathieu Bouchard. I'm the product manager for the surface eddy current array probes, and this is what I'll be talking about today. So, how we use eddy current array for the detection of chloride SCC, so chloride stress corrosion cracking, specifically in stainless steel. So through the presentation, I'll be introducing what we have done for carbon steel because we have you guys have already heard me talk a lot about how we use eddy currents for inspection of carbon steel. But today I'll do things differently and I'll talk mostly about stainless steel. So the rest of the presentation will be talking about SCC, pitting, inspection of small pipes, and detection of internal flaws also in stainless steel. So to introduce, as you know, the spine is a product that we've advertised a lot in the past few years. It's been used mostly for the inspection of carbon steel pipelines. So we use it to detect stress corrosion cracking and hardness also in the pipelines. So this is a probe, an eddy current array probe with 128 channels, so a very wide coverage of 200 millimeter or 8 inches in one pass. This can move at a speed of 2 feet per second, and it can inspect any pipeline diameter of 6 inches and more. So the probability of detection, we've done a lot of studies, a lot of papers published on this. We have shown that the POD was higher than magnetic particles because this is an automated scanner. You don't have to rely on the visual interpretation of data. You don't have to rely on lighting and all that. So it's just an improved version of magnetic particle in that regard. And finally, you also get digital data. So if you want to look at the data 5 years later, it's very easy to find it back and interpret all the data. If any of you don't know this technology already, this is just a quick demo of what a report can look like. So all the indications of SCC and cracks are displayed in red on a green background. So this means that locally where you have red areas, you get indications and you need to go back there locally and either repair or characterize the stress corrosion cracking. But the question now that we get asked more and more when people understand this application in carbon steel is, can we use the same technology but for stainless steel instead? And so just to introduce the differences between the two types of stress corrosion cracking, in the case of carbon steel, we talk about transgranular SCC. So this happens in susceptible alloys, for example, X52. I could name 10 alloys here, X60, X40, X42, BA, all these carbon steel alloys that are older and susceptible to cracking under corrosion. When they're put with a lot of tensile stress and there's infiltration of water that creates a corrosive environment, this is where the SCC develops. And it develops really by crossing the grains. And this is why we call it transgranular. In the case of SCC in stainless steel, this is different. This is what we call intergranular. So the cracks will follow the edges of the grains, and we'll have these more less linear orientation of the cracks themselves. So this happens again in susceptible alloys. In this case, this is typically austenitic stainless steel. Again, you need some high tensile stress in the steel to induce cracking. But finally, the main difference is the agent that initiates the cracks. In this case, we need oxygen and chloride ions. And when you have also high temperature, it creates an even more susceptible environment for cracking. So this is kind of a differences between the two initiators of the cracks. So how does it translate into eddy currents? We developed, for the same spine scanner, we developed two sets of coils. So those at the bottom you see here, it's just a ribbon of sensors that you can attach to the spine. So if any of you have been using the spine for carbon steel, all you got to replace is this little ribbon of coils that is optimized now for stainless steel. So we repackage the coils in a different geometry. We use slightly larger coils to be able to penetrate the stainless steel, and we also arrange them in a different what we call topology. So we move them in a different positions to be really optimized for intergranular SCC in austenitic stainless steel. And we developed two of those probes. The first one is a low frequency If you're familiar with eddy currents, you know that when you are at low frequency, you will allow the penetration into the wall. So you are able with this probe to inspect the ID, so basically internal flaws. You inspect from the outside always, but you penetrate the wall and detect cracks in the inside. And with this second ribbon here, it's the opposite. So you also inspect from the external side, but you bring your eddy currents at the very top surface to inspect for uh, SCC on the external side. I see we have questions here. I'll go through the presentation, and at the end, I'll have 5 minutes to go through the questions. So the first trial we did was on this little piece of pipe. This was, I would say, a very trial for us because the cracks were very massive. They were very deep and very dense. So for eddy currents, you get a very nice green background with obviously the red indications corresponding to the crack. So you see here this kind of inverted C shape. You get the same thing here. So if you follow exactly all the cracks, you will find the same type of geometry. But again, this was not a big challenge for eddy currents because the cracks were so dense and so deep. So we pushed a little bit further and we went through different trials. And at some point, we were able to characterize what is the smallest flaw, smallest defect, external defect that we could find in stainless steel. And we basically put a number of around 2 millimeter long and 1 millimeter deep for this smallest flaw. And this is with a very high signal to noise ratio in a real life condition, in real life pipes. So of course, depending on the amount of corrosion, coating, surface roughness, surface condition, this number will change. We've done projects where we could find 1 millimeter long cracks, and some projects where it was more difficult because there was a thick coating on the pipes. So this was another trial here with just artificial defects on a perfect surface condition, stainless steel 316. In this case, like I said, we were able to find 1 millimeter crack. So this is a very uh, high resolution probe that allowed to find very small indications, very small flaws. Now, one question also that we wanted to validate is whether we were able to detect pitting corrosion. So you know that, as I explained, you need the presence of a corrosive environment to initiate cracks. So when you have pitting, this can be a local site for initiation of cracks. So there's high value in being able to inspect a pipe and know whether or not if it has pitting corrosion or not. So if I zoom on this piece of pipe here, you can see that these little pits here and there, they are detected very easily with the spine. So you see them as very tiny indication. Just by looking at the amplitude of your signal, you know that those amplitude and those indications are not cracks. They're not SCC. They're not very important or not very deep. But you know at least that there is some indications of pitting. And the boxes that are here on top of each pitting, they are put there automatically by the software. So you don't have to go through your long data file and report each of them. They are all automatically put on the C-scan, and then you can just report them all at once. Otherwise, it would be very long. It would be just like in visual inspection. We've also investigated if we could detect pitting on top of a coating. So here you have a very smooth coating of about 3 millimeters on top of a stainless steel pipe. And just the same way, eddy currents, this is the nice advantage of eddy currents is that you can inspect through coating. So the magnetic field will propagate through the coating, and you'll be able to detect those pitting through coating. So this was just a very similar type of results where you see all these little red dots corresponding to pitting. And once again, we did the same thing with pitting as we did earlier with the cracks. We were able to produce artificial flaws and validate that even half millimeter depth were quite easy to detect with the spine when the surface condition of the stainless is very good. So, and 0.5 millimeter here corresponds to about 20 thousandths of an inch. I said at the beginning of the presentation that the spine can only inspect pipes that are 6 inches and up, so 150 millimeter diameter and more. We also have this scanner, this kind of bracelet that you can wrap around smaller pipes to go down to 1.5 inch. So just like on the picture here, we have this little container. We wrap the pipe, or we wrap the probe around it, and very similar type of results. You see the cracks and the pitting in bright red on the green background. And finally, this is a very, I would say, new type of inspection that we can do with the spine, because we just launched this low frequency probe that can penetrate through up to 6 millimeter of stainless steel. So for any type of stainless steel walls, 6 millimeters and less, we are able to use the coils at a lower frequency, make a magnetic field that penetrates through the wall, and you are able to detect basically any type of missing materials. It could be SCC, it could be cracks, weld flaws, corrosion, again, large pitting. So you don't have the same type of resolution, obviously, as on the top side, but you are able to find down to 20% depth any type of surface flaw. So here in this example, you have this same bracelet that we wrap around this section of pipe, and on the inside, we were able to see visually that you have these corrosion wall loss 1, 2, and 3 that we could detect very well on the C scan. So again, this is a green background, number 1, 2, and 3. You notice that they are mirrored because you're looking from this side, but the indications are on this side. So it's like looking at a mirrored screen where your 1, 2, 3 are in the opposite direction, just because this is a far side. So then size to a certain extent, the depth of those indications, if you need to approximate the size, if, for example, you can tolerate up to 50% wall loss is fine, but not more, you can build a calibration curve and try to approximate the depth of those indications. So again, in stainless steel, detection starts at 20% wall thickness. So this is my last slide. If we summarize the performance of eddy current array in stainless steel, the cracks we were able to detect down to 1 millimeter by 1 millimeter. This will depend on the surface condition, but in the best cases, we'll be able to find this. Pitting corrosion down to 0.5 mil by 0.5 mil. Detection of 20% internal flaws in 6 millimeter walls, so up to 6 millimeters. If we have a 20 millimeter wall, we can build something custom, something different that will penetrate even more. But then on the other hand, you will always also lose resolution. So there's always a trade-off between how much penetration of the wall you do and what is your resolution for small flaw detection. The scan speed is up to 600 millimeter per second. You can inspect, as we showed, through coating. There's no requirement for paint, oil, gel. There's no consumable with this probe. So you put the probe directly in contact with the steel or directly in contact with the coating, and you start your scan. Minimal surface preparation, depending again on the coating thickness, and you get digital data of the C scans. So thanks for being here. Thanks for asking the questions. I will go through them right now. Just before I finish, we just published March 28th. So yesterday we published this blog. My colleague Phil Mackay wrote a blog on this exact topic, showing giving a little bit more details about what I talked about today, comparing eddy current array to penetrant testing, showing some scan results that we've got with this probe. So if you're interested to learn more about this, just go on our website. We have a blog. The latest blog that we've released is on this topic. Okay, let me check the questions now. So number 1, hello, for spine, are there any detection limitations for circumferential cracking, or the crack orientation has no influence? That's a really good question. I didn't mention it, but it has no influence. So with spine, we also always use 2 types of channels. We have the axial channel, they will detect flaws that are actually oriented, and the circumferential channels, we detect transverse cracks. So both of them will be detected the same way, same probability of detection. So it's the same thing. Can we inspect pipes at high temperature? Yes, the spine can go up to about 150 Celsius. If you need to go higher, we can even build the probes with different coils that are adapted for high temperature. But for the spine, we have been using it up to 150, and even in some cases on 180 degrees. So around those, yeah. Can we also use the technology to detect internal corrosion? Yeah, I presented it at the end. In our case, it was wall loss, but yes, corrosion, SCC, cracks. In stainless steel, you can penetrate, so you can detect all those indications. Is it possible to inspect epoxy-coated pipes? Yes, the epoxy coatings are very smooth and very thin. So with spine, we can tolerate up to maybe 3 or 4 millimeters of coating, of epoxy coating. In carbon steel, what is the maximum thickness of penetration? Okay, so what I presented here for penetration is only specific to stainless steel. Carbon steel has very high magnetic permeability. We cannot penetrate anything. So the penetration in carbon steel is 0. We are only sensitive to the top surface indications, so external cracking, no penetration. Did subsurface indications inside weld possible to detect? Yes, again, it depends on if the weld is magnetic. If you put a magnet on the weld and you can attract it, it means it's like carbon steel, there will be no penetration, not possible. If it's stainless steel, the weld is not magnetic, yes, we can definitely penetrate the weld, and we have done this kind of projects many times where we inspect circumferential welds in two stainless steel pipes. We have this scanner that goes around, and you can detect internal welds flaws, no problem. All right, thank you for all the questions. It's really nice when people are asking questions. So thank you for being there. The video will be accessible on YouTube. So have a good day. Take care.